Reavis is a lecturer in statistics at King's College London. She did her master's degree at Politecnico di Milano and her PhD at the University of Cambridge. She then took on positions as a postdoctoral researcher in King's College London and a visiting researcher at the Alan Turing Institute before moving to her current lecturing position at King's College London. Her research interests are in computational statistics, probabilistic machine learning, Bayesian inference, and medical and engineering applications. And you can really see the high quality of her work when you look at her publications on her Google Scholar. For example, the optimal thinning of MCMC work that she'll talk about is going to be published in the really highly regarded JRSSB, or Journal of the Royal Statistical Society Series B. So thank you very much, Marina, for coming to talk with us today. Please take it away.
Thank you very much, Leah, and thank you very much for the kind introduction and for inviting me to give a talk at the Bayesian section of the Statistical Society of Australia. So as I said, today I'm going to be talking about my work on optimal tuning of MCMC output, and in specific on the cardiology application and cardiac electrophysiology application that we started with back then. This is work in collaboration with lots of people. You know some of them, and other people in your group may know some of them. So Wilson Chen, John Cocaine, Pavel Svetak, Steve Niederer, Lester Mackey, and Chris Oates. So I'm going to give a brief outline of the talk. I will give a motivation and introduction for why we started this type of work. And then I will talk about what we mean specifically by optimal tuning of MCMC output, which consists of two parts mainly. So defining a measure of quantity that we want to optimize. So choosing a discrepancy between probability measures and then how we optimize it. And then I will show some theoretical and empirical results and conclude. So just a bit of introduction and where I started. So I started this project, which was jointly funded by the British Heart Foundation and the Alan Turing Institute 3.5 years ago now, in a group that was working on computational cardiology. And by that, I mean that they still work and they still create multi-scale and multi-physics models of the heart. And this is very much in line with the vision that the UK and other countries have now of digital twins, meaning a digital and computational model that is continuously updated through time and through different integrated measurements of any entity, which might be a physical entity, it might be a cyber entity, if we think about cyber twins. In this case, what the goal is to have uncertainty quantification and propagation through different scales and physics, so from the cell to the cardiac tissue to the whole heart, in a way that is personalized to each single patient, so that helps both diagnostics and prognostics for different patients. Now, as you can imagine, the computational complexity of these models increases as we go through scales. And at small scales, for example, the cellular scale where I was working, it is possible to simulate the model quite quickly. So it is possible to think that if we solve, if we treat the numerical solution of the solver as exact, we can perform MCMC. We can in theory perform MCMC. What's difficult is to assess the quality of the samples, as you will see from the plots that I will show in a minute. And that comes in a bit of a clash with the fact that even if we can perform MCMC, we have a finite computing budget. So we need to be able to stop simulations at some point because time or money is running out for running the simulations. The other thing that I said, yes, it's computational complexity increases through scales. And if we want to perform uncertainty propagation, we need to be parsimonious in the parameters that we use to propagate uncertainty. And so in a way, we want to compress samples to use them in an experimental design fashion. So to give a bit of background on the biological model that I was using, it's this hinge model. It's one of the possible models that are used in computational in electrophysiology. There are many of them. I did not choose this model. I was told to use this model, but one of the reasons why it was interesting is that it's a quite complete model that takes into account different time scales which things happen. So what happens is that calcium comes in a cardiac cells. It triggers a release of calcium from an internal bag that is within the cell that circulates in the cytoplasm. It contracts to different proteins, and then it goes out from the cell again and goes back into this bag of calcium. And so this specific model was incorporating more subtle time scales at which things happen. There are 6 state variables in this model, but only one of them is observable in our experiment, which is this internal cytoplasmic calcium. So it's a partially observed model. In terms of data, people in Oxford were performing experiments, and they analyzed of the order of 20, or at least we were left with 20 good data traces. So what they did is they stimulated cells using a patch clamp experiment by applying certain voltages and stimulating the cell with a drug, caffeine in this case, in order to enhance system identifiability. So each of these parts of the protocol was meant to stimulate specific proteins along the lines of those that I was showing before, in a way to hopefully help to infer the parameters. So it was designed by biologists. In black here, I'm just showing one of the specific cell traces that I will be focusing on in the talk, but we had 20. From a statistical point of view, we did model things as simply as possible. So we said, well, the cell model can be represented as a set of as a system of couple ODs, in which we have an unknown parameters, fairly high dimensional here, so it's 38-dimensional high parameter, we assume we had an unknown initial condition, meaning that we were running the solver for long enough to get to a steady state each time that we were solving and running the MCMC. In terms of data, we modeled them as a Gaussian additive noise on top of the ODE, so that we can formulate the likelihood simply as Gaussian, and the nonlinear part is in the ODE solution. We said, well, the variability in the cell response, being Bayesian and being statistician, can be explained by thinking that each cell corresponds to different parameters, X in our notation, and being Bayesian in this sense makes sense in the sense that we can, it allows us to model expert-derived priors on the parameters. So there is quite a vast literature on those parameters that gives a fairly good idea of where they should be at least centered. And it also enables to model quite nicely system identifiability in contrast to any optimization procedures. That's something that people in this field do as well. So they try to fit single points for the parameters. So just to fix a bit of notation, I know this is a Bayesian group, so I'll go quickly through this. The goal was to sample from the posterior distribution, where P of X is an appropriate prior density, and the normalizing constant is an intractable d-dimensional integral. As we all know, it is possible to sample in theory from P using MCMC if and again, I'm treating here the solution of the solver as an exact solution, so we're not modeling any numerical error here. But so if we do that, it's possible to treat the likelihood as tractable, and then sample from the posterior distribution using MCMC. However, as we all know, MCMC out of the box faces some challenges, especially in high-dimensional setting, and this is what we face here. So in particular, to give an idea, we have indirect evidence about the fact that the parameters were coupled together, and so they leave the manifolds of the parameter space. For example, if we consider the Fisher information matrix in a point of the parameter space, and then we prior precondition that and threshold it, we find blocks of dependent parameters, or we have evidence that there are blocks of dependent parameters in different points of the parameter space, and this type of matrices change along MCMC iteration. Some other challenges regarding MCMC and what I was trying to do a few years ago now was, well, we said, let's try to use the fact that we can solve the ODE system by computing sensitivities, and so solving an adjoint system and finding gradients of the posterior. So that's hopefully going to give us a better proposal in the MCMC. That can perform poorly, so it's still quite hard to tune. And besides, it does require higher computational costs, so it didn't really help us. And then we also need to consider the fact that the ODE solver can fail in specific values of the proposal, and it's quite hard to decide what to do online when running MCMC. So an easy solution for us was to say, let's reject the values of the parameter where the solver fails. But it's kind of hard to assess the bias that this introduces in the procedure. So just to show a bit the type of MCMC traces that we got, after a few weeks of running the MCMC with simple adaptive random walk, meaning that for some iterations we were adapting the step size of the proposal, these are the trace plots for the first 8 parameters. And as you can see, there is no clear behavior that we would like from, or in an MCMC that has converged, which is this fat caterpillar behavior. However, there is information, and there is important information in this data. So if we fit the model, and we did the same experiment by using just part of the data and then using the rest of the data to compute the proper posterior predictive distribution, there is still some information here, in the sense that there is a nice contraction of the posterior with respect to the prior. I'm not showing prior fits, but in this plot, but they will be all over the place basically. So there is information gained. And so the question was what we can do, given that we have finite computing budget and we don't want to spend any more time into refining a proposal that is tailored specifically to our problem. And that led to this notion of optimally tuning the MCMC output. So just briefly to generalize the problem, what we want to do is to remove bias from MCMC that can be introduced, that is introduced in the burn-in stage of MCMC, and by the fact that MCMC might have not converged properly to the distribution. And we also want to provide a compressed representation of the output, again, with this idea of uncertainty propagation through different scales of the model. And so we will call P our distribution of interest as before, and Xi a set of samples from a p-invariant Markov chain for the first part of the talk. As we know, if we don't post-process the MCMC output, we can approximate P with the empirical distribution that is equally weighting each of the points sampled by the MCMC. And as I said, so this introduces bias if the chain has not converged, and it also suffers from correlation. So specifically in this plot, we can see that because of correlation among the samples, the chain has explored more one of the modes, even if the P is a mixture of Gaussian distribution that gives equal weight to the two modes. So something like that can happen, and then this introduces further bias in any Monte Carlo estimate that we can derive related to P. Traditional post-processing of MCMC estimate in a way, and I will mention later on some literature on how to do that, estimates in a way the parameter B burn-in, and then tunes the chain every in a fixed lag fashion. So every T sample, it retains every T samples, and then it's true that using this approach tackles bias, but it does increase variance if this parameter B is very large, because it discards most of the samples from the chain. And it's also known, so there is a famous Geyer paper that shows that tuning also tends to increase the variance if we think about having infinite computational budget. So what we wanted to do was to find a set of indices and of points that we will retain. So it's these M points ideally much smaller than n, again, with this idea of uncertainty propagation, so that we will approximate our posterior distribution with an optimal empirical distribution. So the red points will be an optimal approximation of our original P. The red points, I said, yeah. And this notion of optimality can be translated in the following way. So we would like to find this set of indices by minimizing a notion of discrepancy between the empirical distribution that we retain and the target distribution under this constraint of fixed cardinality of the set of points that we retain. And so what one needs to specify in this framework are what type of discrepancy can be used. And it has to be a computable discrepancy, and also meaningful in a way that I will specify. And also what type of optimization procedure is used to solve this problem. So that's what led to Stein thinning. So hopefully this diagram is not confusing, in the sense that what Stein thinning does, and this optimal thinning of MCMC output, is to solve a problem of MCMC post-processing in an optimal way by using tools of quantization of probability measures that were developed in different literature by some of my co-authors. But in a way that was either optimized, that was mainly optimizing freely this measure of discrepancy in the parameter space, while we constrain that to be on our MCMC output. And hopefully you will understand a bit better as I go through the details. So step one, we need to choose which discrepancy we use. So it's quite common to, in machine learning, it's quite common to consider the notion of integral probability metric, which by definition is the worst integration error so we have two probability measures, right? Q, which in our case will be this empirical distribution, and then P. And so an integral probability metric is the worst integration error when we consider integrating against Q versus integrating against P over a class of test functions that is large enough to be measure determining, meaning that if the IPM is 0, then this is equivalent to having Q being identical to P. So we can think about this as, in a way, as a generalization of the method of moments, and that's why it makes sense to use this definition. However, there are two computational problems in using this definition, which are simply in Bayesian settings, it's quite hard to compute these objects, so integrals against the target distribution. And it's hard to solve these optimization problems. So we need to find a supremum over a very large class of functions. So it's an infinite dimensional optimization problem. And the solution, again, in typically machine learning literature, but slowly this is, machine learning and statistics, let's say, comes from the freedom in choosing the class of test functions F. And in particular, I will show what choices of F lead to the notion of Kernel Stein discrepancy, which is what we use in this work. I will ask you to have a look briefly at this diagram, and then I will recall it a bit later. So if we start with our IPM, and we said from a computational point of view, we have two problems. So computing the supremum and computing this integral. By choosing F to be a specific type of class, we can get rid of this supremum, but we're still left with intractable integrals against the target. By choosing F in a different way, and that leads to a notion of maximum indiscrepancy. By choosing F in a different way, and I will again specify what these elements are, we can get rid of intractable integrals against P, but we still have the problem of computing the supremum. And then it's actually possible to see that we can combine these two elements to get a notion of discrepancy now. So it's not a metric anymore, it's a discrepancy that is computable, but besides being computable is also meaningful. So I will show this in a moment. So first of all, the class of F that leads from an integral probability metric to a maximum mean discrepancy. It's that class of F, as we will see, is the unit ball in a reproducing kernel Hilbert space. And to define what I mean with that, we need to introduce a notion of kernel, which is a symmetric and positive definite function that goes from the Cartesian product of the input space into R. And we can say that K reproduces a Hilbert space of functions if once we fix one of the arguments to the function K, that function belongs to H. And if any function evaluation can be represented as a dot product between K and F in this Hilbert space. And there is a one-to-one mapping between kernels and Hilbert spaces. So in a synthetic way, we write H of K. And so, as I was saying, so choosing the set F to be this Fk, so the unit ball, the set of functions that have norm bounded by 1 in the RKHS enables to write the to get rid of this notion of computing a supremum, and instead of that computing norms in the RKHS, and it leads to this notion of maximum mean discrepancy. It's possible to show that this is a metric. Under suitable condition, this is a metric on the space of probability distributions on X. And also that if these maximum discrepancies goes to 0, then we have weak convergence of Q to P. So, this will be a first step. So a first way of finding a more computable distribution. However, as I was saying, this still leads to sorry, to having to compute. Sorry about that. Integrals against P. So on a separate way, what we can do is to compute Stein discrepancies. And so to introduce those, I will first mention what's the Stein's characterization of a probability distribution. And we can say that the distribution P can be characterized by an operator AP and a class of functions G if it holds that mappings of any functions G belonging to our set calligraphic G through the operator AP integrate to 0 against the distribution P. And so this is the Stein characterization. Stein's identity, Stein's discrepancy, in a way, it's a deviation, it's a maximum deviation from Stein's identity if we consider the same integral, but not against P, but against any distribution Q. So that gives a notion of discrepancy. And if we make the change of notation in which we call mappings of G through the operator AP calligraphic F, now we can recover a class of test functions to be used in that initial definition of IPM, integral probability metric, right? And to combine these tools, so reproducing kernel Hilbert spaces and Stein discrepancies and Stein's method, it was shown, and I will use the notation that is useful to use in a one-dimensional case, but this can be generalized. It's possible to show that under specific conditions, if GK is a unit ball of a given reproducing kernel Hilbert space, and if we use a specific Stein operator, but there are several types of operators that could be used, then the resulting space, so AP, the mapping of AP times this initial kernel, the mapping through AP of this initial kernel leads to a new unit ball of an RKHS. And so what we can say is that integrals of functions that belong to this new space map to 0. And this new space, as I was saying, so it's an RKHS with a new kernel KP. So in the following, what we will have, we will be using this specific space of functions, and we will have, so this base kernel that comes from the initial RKHS that we map through the Stein operator, and then we will have this KP. And one thing that I would like to ask you to pay attention to is the fact that this KP is computable once we fix the kernel, the base kernel K, and once we have, so this quantity is the gradient of the log posterior, so it doesn't depend on the normalizing constant. And so in a Bayesian setting, this is a computable quantity. So going back again to our graph, so hopefully this makes a bit more sense now. So what we end up with is this notion of Kernel Stein discrepancy, that in the case Q is an empirical measure, takes the form of just summing the element of a Graham matrix on the specific set of points that we have, and in this case, those are the points belonging to the MCMC output. And as I was saying, KP, so this matrix does not depends only on evaluation of a base kernel K and gradients of the log posterior, so it's something that we can compute. On another hand, the KSD control convergence in a way that, and this means that under specific regularity conditions on P, we have that if the KSD between two different probability measures goes to 0, well, in this case between the empirical and P goes to 0, then we have that the empirical distribution is converging weakly to P. And so from our optimality point of view, it does make sense to try to find a point that minimizes this Kernel Stein discrepancy. This theorem was proved when this base kernel is so-called heavy tail kernel, so a specific type of kernel, so this inverse multi-quadric kernel that has a parameter gamma that needs to be tuned somehow, and that affects the performance of the algorithm. I will show this later, but in a way, this gamma has to measure a notion of distance of points in the input space, so between our parameters. So it does make sense to minimize the KSD, and we need to choose gamma, as I was saying. So step 2 in our optimality procedure and optimization procedure is how to optimize the KSD. And so what we went for was a greedy approach, and this was shown to perform well in previous work that worked on the notion of quantization of probability measure, as I said. So we went with this type of optimization procedure. We also proved theorem based on the fact that points were selected in a greedy way. So given our MCMC output and a kernel KP that now we know how is fixed, the set of points that optimizes the KSD with fixed cardinality is obtained by selecting the first point to be the posterior, approximately the posterior mode, and then scanning the MCMC output in a way that the KSD is minimized. That's the point that minimizes the KSD once we add that point to the previous bag of points. So it's this greedy procedure. It is possible to show that the cost of this method is comparable to the cost of producing the MCMC output. So it's upper bounded by n, where n is the length of the MCMC output times m squared, recalling that m is the number of points that we retain. However, in practice, it's much faster to run the Stein tuning procedure compared to running the MCMC. So in our cardiac case, for example, running the MCMC took a couple of weeks. Running Stein tuning took of the order of half hour, maybe. So with a cardinality of m of the order of a couple of 100 points that we're retaining. And it's also good to notice that the same point can be selected more than once if that point is very useful to represent the posterior distribution. I will just have a small note about the fact that this is what we later on called a myopic approach, in the sense that we're selecting one point at a time, and a no mini batching approach in the sense that we scan the whole MCMC output, but there is extension of this work to improve the computational, to improve the speed and performance of this type of optimization procedure. So this is another paper. Great. So I was hoping to have this video work. So let's see if it does. So let's say that we have our intractable probability distribution. The black points here are points belonging to an MCMC output. As we see, MCMC is exploring a lot this lower mode, but not that much this upper mode where actually most of the probability mass is located. And so this is a scenario in which we can think that MCMC has not converged in a proper notion of convergence. And so what Stein tuning does is really correcting the bias introduced by both Bernine, which here it's not present, but Bernine and correlation. And so producing this set of points that corrects the MCMC output. I'm going to stop this now. Corrects the MCMC output to better represent the posterior distribution. So this is what the whole method does. In terms of results, so I will talk briefly about some theoretical results and then show some empirical results. So we managed to prove and to give guarantees of consistency of the empirical distribution that is obtained after Stein tuning by considering the type of optimization procedures, in this case, greedy optimization of the KSD, the fact that the MCMC itself is a stochastic procedure, so there is randomness inherent in the MCMC, and also considering a possible bias in the Markov chain. So, result number one, if we first think about having a fixed MCMC output, so there is now no notion of randomness in these set of points x1 to xn, they're fixed and their length is fixed. What happens if we Stein tuning setting m to infinity, so the number of points that we select? It's possible to show that the KSD between the empirical distribution thus produced and P is upper bounded by the KSD between what we can call the optimally weighted empirical distribution, where with optimally weighted, we mean a distribution that is assigning weights that are constrained to sum to 1, be positive, and they optimize, they minimize the KSD between this empirical distribution and P. So our KSD is upper bounded by that optimally weighted KSD plus a term that is vanishing as we set m to infinity. So what happens in practice is what I'm showing here is the KSD along an MCMC output, actually the one that I was showing in that cartoon plot with the mixture of Gaussian distributions. So what happens is the gray line is not optimally selected points. So what we're doing is just giving the same weight to each one of the points of the MCMC. So we have to stop at some point. The black line is Stein tuning, so it's producing points coming from Stein tuning. So now we can set m as large as we want, right? The red line is the KSD of the optimally weighted empirical distribution. And so what happens is that those two lines will hit a threshold. So we can't set them to 0 because the MCMC output is fixed. So they will hit a horizontal asymptote. But what happens is that this Stein tuning measure will converge to this optimal measure that we can compute. So the Stein tuning points will go to these optimally weighted points. So what those are doing are giving a weight to each one of the MCMC outputs. And so they have higher computational costs. So they relate to this notion of Stein importance sampling. Well, what we're doing is really compressing the output and then giving the same weight to each point. The blue line is if we could consider the weights to be negative, but we're not considering that here. So that was our first result. So we can't really hope to set the KSD to 0 if we fix the MCMC output. However, we can do that if we consider the fact that the MCMC output is random. And before talking about that, I will just quickly recall what we mean by the uniform ergodicity. So it's possible to define the V norm of a function and the V norm of a measure in the following way. So we define a function V from the input space to this set, so 1 to infinity. And so it's possible, yes, I was saying it's possible to define V norms of a function and of a probability measure. And so what we can define a notion of uniform ergodicity, which is similar to the notion of geometric ergodicity, except that it has between the distribution of the law of the endpoint of the MCMC output, right, and the target distribution, which is similar to the notion of geometric ergodicity, except that it has this V function here, and we're computing the V norm between the two probability distributions. If we consider this notion, then it's possible to prove an L2 convergence result for the KSD on the random MCMC output. So we think about having a chain that is targeting its P invariant. And we consider a function V, which is upper bounded by the square root of the kernel KP. So it's possible to show that the expected value of the KSD, which is now a random variable because we're considering this MCMC output to be random, right? So the expected KSD square is bounded by a term which is now vanishing as we set both M and N to infinity. And moreover, this result gives a non-asymptotic bound, which is also a non-tight bound on the expected KSD squared if we think about fixing the MCMC output. However, this is not enough yet to show. So the fact that the expected KSD square goes to 0, it's not enough yet to show that we have consistency. And so our final result does that by allowing an extra step, which is allowing to have a Markov chain that is not targeting the initial distribution P, but it can target even a distribution Q such that P is absolutely continuous with respect to Q. So we don't necessarily need to target our initial distribution, but we can. So now no one forbids us to do that. And under, again, regularity conditions that I'm not reporting here, but they're in the paper, it's possible to show that the KSD, which is again a random variable, converges to 0 almost surely, again, as we set both M and N to infinity. And this almost sure convergence guarantees that this empirical distribution, which is again a random measure, converges weakly to P. And because this is random, now we need to specify in which way it converges to P. So we need to add this. We can add. It's possible to add an almost sure notion to it. So this is a very important result, and this is what we used in practice in our simulations. And I will show that by choosing a distribution Q, so a target distribution Q, which was a tempered version of P. So an easier to target distribution Q if you want. So that said, so this concludes the theoretical results. In terms of empirical results that are in the paper as well. So we started by trying to do a bit of experiments, again, trying to solve inverse posterior inference for systems of ODEs. Again, running a simple random walk MCMC. And then we compared different types of MCMC post-processing. So traditional thinning, which is based on identifying burn-in based on these R-hat convergence diagnostics by Brooks and Gelman, and then modern versions of it. And then we compared support points, which does in fact, it does a similar has a similar approach to Stein tuning, but it optimizes a different notion of discrepancy, if you want, between probability distributions. And then Stein tuning based on different choices of the kernel K. And again, I have details on these, but they give notions of distance, again, of how distant points are in the parameter space and samples are in the parameter space. So this is a metric gamma, so it has this notion of distance for each couple of parameters. And what we compared are two measures of performance. So the energy distance, which is the quantity that support points is trying to optimize, and the KSD based on one setting for gamma. And so we compared the energy distance as well, so that we were not biased in our performance measure. We started with a small dimensional sample, with a small dimensional model, so it's Goodwin oscillator with 4 dimensions. And what I'm showing here are the Markov chains on a log scale. So it's intuitive, and it's intuitive to think that the MCMC has converged here by looking at the fact that after a number of iterations, the space explored stays the same, right? And it's converging. It has converged quite quickly. But what I'm showing below is this R hat statistic, convergence diagnostic, sorry. And I'm showing different versions of it. As I said, there are a number of choices of hyperparameters and to be made when computing these R hat. But in principle, what happens is that one needs to compute it and then decide a threshold. And in practice, discard the points for which this R hat is above the threshold. So the threshold related to the red line will be here. So we will be discarding a lot of points. To the blue line, somewhere here, right? And the black line has not converged with respect to any threshold. And so what happens here is that having this approach tends to suffer this bias variance trade-off in a fixed N scenario, in a sense that, as I was saying, we can think that the MCMC has converged here. However, this R hat statistic and this approach, it's inducing us to discard most of the points, and what we would need to do to have a good quality or long enough chain will be to run the MCMC for longer and then keep more points and then tune those, right? However, we're assuming that this is not possible in our initial computational model and that we have a fixed budget, right? So we can't keep running the MCMC for longer and longer, or we think that we're in that scenario. So in terms of performance metric, on the left-hand side here, I'm showing the energy distance, and on the right-hand side, the Kernel Stein discrepancy. The gray and black lines are traditional tuning and support points, and the color lines are Stein tuning. Hopefully, you can see the colors. So what happens is that Stein tuning is performing comparable to traditional tuning and support points with respect to the energy distance, and of course, is performing better with respect to the KSD. However, it's important to notice that this notion of energy distance is not sensitive to details as much as the KSD is, and it also does not provide convergence control. So we do a similar job with respect to this metric, but support points are not guaranteed to provide an empirical distribution which is converging to P. With respect to the hinge model, so this cell model that I was showing initially, if we look first at this right-hand side column, so in black I'm always showing the prior distribution for the first 3 parameters, but you can think about 38 parameters, right? So black lines are the priors. Color lines here are MCMC runs. As you can see, they're stuck in different modes of the parameter space. And so running simply MCMC would introduce bias in approximating the posterior distributions. So what we did on the other hand is in these three other columns, I'm showing MCMC, which is targeting a temper posterior. So here MCMC is not targeting a temper posterior, it's targeting the true posterior. What I'm showing here is MCMC targeting the temper posterior and then post-processing that MCMC with stenting and what we can see is definitely consistency among MCMC runs. And we can also see that we did learn something from the prior. So the posterior is more concentrated than the prior. It's natural to ask the question, and this is quite consistent against when changing this preconditioner gamma in the kernel, right? So it's quite natural to ask if this is happening because we are targeting a temper posterior or not. And so what we considered is computing the KSD. Now, it was not possible to compute the energy distance because that requires a high quality MCMC run, which we didn't have to start with. So what we're comparing here is the KSD of stenting, again, in color, and then support points. So it's this other method, which is based either on the original MCMC output, is this gray line, or on the tempered MCMC output, and this is this black line. And so we think that support points based on the tempered MCMC outputs has higher values because it's this tempered MCMC output is biased, right? And so support points that builds on that introduces bias in approximating the posterior, while on support points based on the standard on a non-tempered version is also biased because we're just the MCMC is getting stuck in one of the modes of the posterior. So this gives an indirect idea that stenting, that doing this combination of tempering the posterior and then stenting the output actually allows to achieve a consistent approximation. But of course, one would need to run extensive simulations on this. So in terms of biological conclusion, just as a bit of curiosity, so what we found, and so what we did was to repeat this experiment. So for one cell, what I'm showing here are box plots of the prior versus posterior distribution. And then what we did was repeat these experiments for all the 20 cells that we had at hand for each one of the parameters. And what I'm showing here is this ratio between posterior versus prior standard deviation, just as an indication of posterior contraction. And so the smaller and the brighter is this point, the more we learned about these parameters, the corresponding parameters independently. The whole goal was to try to actually work on a hierarchical Bayesian model for these 20 cells. However, the parameter space is really large with respect to the number of points that we have. So 20 is not really enough to constrain this. So hierarchical Bayesian modeling was really biased by the choice of prior that we were making. And so what we did was really to compute correlation matrices along MCMC and then average those as an approximation to the full correlation. And so we managed to find blocks of correlated parameters that have a biological meaning in the sense that they talk about proteins on the cell membrane and then proteins within the cell. And the two blocks, so each of these blocks, so the parameters in each of these blocks are positively correlated, but the two blocks are negatively correlated. And this suggests, again, this compensatory mechanism between activations of proteins on the membrane and then within the cell. And so this is the biological finding that we had. And so just to conclude, so some of the advantages of the method that I showed are that it allows to automatically identify and remove the burn-in from the MCMC output. And at the same time, it offers a compressed representation of the posterior distribution. And as I showed in that theorem 3, we can remove bias for bias sampling procedures. So we can target something that is simpler to target and then post-process and correct the bias that is intrinsically introduced in that way. some caveats. So the conditions, I didn't show the conditions in the theorem, but they say in practice that the MCMC needs to have explored at least once regions of high posterior probability distribution under P, because otherwise we can't really correct that. We do require gradients of the log posterior density, so this might be expensive to compute, but once the MCMC output is realized, then we can just do that in parallel. There are some pathologies if P has very far away regions to which assign mass. And this method is also not invariant to reparameterization. So one needs to decide prior to starting the whole procedure what type of parameterizations to use. And so with that, I will just like to invite you to have a look at our webpage. So it's under development. This is an old version, apologies for that. So we have our code as well now. And the paper is available online, as Leah was saying, in the Journal of the Royal Statistical Society Series B. And with that, I would like to conclude and thank you for your attention. Thank you very much. And yeah, I'm here to answer any question and start the discussion. Yeah.
Thank you, Marina. That was great.
Thank you.
We'll join with a round of applause virtually. What questions do we have for Marina? I know I've got a couple, but I'll let other people go first. Feel free to unmute yourself. Put your hand, raise your hand. Okay, I can see a couple of hands raised. I think David was first.
Hey, thanks, Leah. And thanks, Marina, for a very nice talk. I had a question about the underlying ODE model that you're dealing with. You mentioned some unidentifiability things that you're trying to deal with this method. Are they things you were able to identify with some sort of structural identifiability a priori, or you were discovering that through the way the Markov chain evolves?
Yeah, so we conclude that, for example, and I'm showing this graph for that. So we did conclude that, for example, the parameters for which prior has not really moved from the posterior are identifiable. Of course, one would need not to look at the original parameter space. And actually, one of my master students is doing a bit of work into looking at transformations of this. So there is work, for example, it's called this likelihood informed subspace, in which one looks at eigendirections of a notion of covariance matrix and then tries to identify that. So it's possible to see them in DOD in the sense that, for example, some parameters appeared in a coupled way, either as a ratio or as a sum, so one can think about that. We really tried to identify all the original parameters, and then this type of plot really gives a notion of marginally, if we look at that original parameterization, what we can think is not identifiable, but one would need to think about non-biological parameters and then work on those. Yeah, but yeah, thanks. It's a very important question, and actually, it's a question very much related to this notion of also sensitivity analysis in a way that people do, and then yeah.
Thank you very much. That was good.
Thanks.
Okay, I think Matt was next.
Hi, Marina. Really, really good talk. Sorry, I'm having issues with my camera. I was wondering, it might be a bit of an odd question, but could you use multiple, could you run multiple chains and still use the method, like on the post-processing of multiple initializations?
Yeah, so yeah, the theory that we developed is not, it's really for one chain, I think. So what I would do is to process each individual chain, but that's a very good question. So you mean by looking at the ensemble of chains, right, as your one big chain approximating the posterior distribution, something like that, right?
Yeah, that's what I had in mind.
What you have in mind, yeah. I will need to think about it. So for sure, processing each chain separately and then probably looking at the ensemble of points would work. But yeah, it's something to think about. Yeah, thank you.
Great, thanks.
So I have, in the meantime, while I'm asking my questions, other people can feel free to put their hands up. But yeah, so my first one is, I understand that so you can do weighting or you can do thinning, and there's several advantages to doing thinning, right? Can you maybe talk a bit about that? I just can't remember.
What was the first thing that you said? So you can do.
What's the advantage of doing thinning versus weighting?
Weighting, yeah. In our case, it was compression of the MCMC output, so it is faster. Weighting has computational cost that is of the order of n cubed. Thinning is n times m squared, so it's faster, but it also gives a compressed output. So and that's really what we wanted. So not really give a weight to each point of the MCMC, but pick the points that are relevant, and then having basically these weights pop up in a natural way. So that's what's happening here. So if you run it long enough, you will converge to that distribution, right? And so eventually you will probably select either all of the points or, almost all of them. But if one has a finite budget and then wants to propagate uncertainty, that's what we were aiming for. Yeah, I hope that answers, but if there is something else, I'll let you know.
Yeah, you did, thank you. The other one is, I think it's so cool that these methods can correct bias. I wanted to know what your thoughts are on, should we stop doing like pi invariant or like p invariant MCMC?
That's another very good question, and it opens up to research, a new piece of research that has not been done already, which would be defining basically this optimal notion of Q in a way that it's optimal, so that you can, and by optimal I mean it's a distribution Q that you can easily sample from. So it's not necessarily just tempering the posterior, it's the thing to do, it might be something else. But yeah, if if it was possible to find a Q such that it's easy enough to sample from, but then post-processing the samples helps in this tinting way, yes, it would be nice. One thing to keep in mind is that the output of this tinting is not an MCMC anymore. So it's a optimally quantized probability distribution, but it does not have this notion of Markov chain anymore. So it depends on the application that you want to use and what properties of that object you rely on. Yeah.
Cool, thank you. Yeah, so I guess we've hit 5. So any last quick questions? Okay, if not, let's thank Marina again for a fantastic talk.
Thank you very much, everyone, and again, Leah, for inviting me, and everyone for being here. So thank you so much, and hopefully see some of you at some conference, hopefully in person.
Yeah, hopefully soon.